Hello. Today I will disassemble this inverter used in unbelievably cheap electric cars made in China. This inverter is used in China's Wuling Hongguang Mini EV. I'm going to disassemble it. Professor Yamamoto, a researcher of power electronics at Nagoya University, kindly lent me this inverter for this video. I would like to take this opportunity to express my appreciation to Professor Yamamoto. We first met at an exhibition, by the way. This is the overview of the electric car. When it was released in July 2020, the low-end model cost 28,800 Chinese yen, which was about 450,000 Japanese yen at the exchange rate at the time. The price when this video is taken is 32,800 Chinese yen. There were some price revisions. The price increased by approximately 13%. In Japanese yen, it's 650,000 now. This inverter drives a permanent magnet synchronous motor. The maximum output power is 20 kilowatts, 85 Newton meters. There is a sticker here with the specs written on it. This inverter's maximum input is 96 volts DC. The maximum continuous current is 140 amps, and the maximum momentary current is 350 amps. The degree of protection is IP67. Dust does not get inside the inverter. You can immerse the inverter in the water for a short period of time. Let's take a look at the exterior. Let's look at the size first. It's about 15 centimeter high and 25 centimeter wide. The depth is about 21 centimeter. Viewed from above, these are the battery terminals, positive and negative. And these three are the output terminals of the inverter. The inverter is connected to the motor with these, U, V, and W. The inverter is connected to the motor with copper windings. The windings run through here and they are secured here. They are secured with a bolt. Let's look at the back side. As you can see, it is a huge heat sink. These are the cooling fins. Each of them is 1 millimeter thick. And the depth is 43 millimeter. The length is 270 millimeter. The inverter cools itself using this huge heat sink. Electric car inverters usually use liquid cooling system, but this one uses only air cooling. It's to lower the cost. This inverter is only 20 kilowatts, so it can be cooled sufficiently only by air cooling. Next, let's look inside. I'll remove the cover. Something fell. This is a rubber sheet placed on the electrolytic capacitors. When you put it on the aluminum cover side, it looks like this. I'm guessing this sheet is used to protect the capacitors from the vibration of the car. It may also contribute to cooling a little. However, this sheet covers the pressure relief valves of the capacitors. The valves are on the upper side of the capacitors. It's a bit concerning. Well, the sheet is not pushed strongly against the capacitors, so I guess it doesn't affect a lot. First, I'll explain the overall structure. This is the heat sink. There's a circuit board that's attached to the heat sink, and there's another one on top of that. Electrolytic capacitors are on this circuit board. And there's another circuit board on top. This is the control board. I'll go into details later. If you look from above, you can see 5 terminals. When the cover is on, do you remember the DC and AC terminals here? They connect to each other. These two are the DC input. These 3 terminals, or bus bars should I say, are the inverter's AC outputs. There's a circuit board on top. This is the control board. There are 2 black donut-shaped things. These are the cores for the current sensors. Let's remove the control board. The control board and the second circuit board are connected with this component. Let's look at the flip side of the control board. There are ICs such as a microcontroller, controllers, and operational amplifiers. ICs necessary for controlling the inverter are mounted here. Let's look at the current sensors. They are soldered here. If you look from this direction, you can see the whole sensors. Here and here. This inverter is for a 3-phase motor. The sum of 3-phase AC is 0 if you ignore the shaft current. So 2 sensors are enough. The microcontroller calculates the current of the remaining 1 phase using the current of the 2 other phases. This is the microcontroller that calculates the current. It's TMS320F28069PZT manufactured by Texas Instruments. A 90 MHz, 32 bits microcontroller. I checked the manufacturers of the ICs on this control board. They are all made by Western manufacturers with proven results. Texas Instruments, on semiconductor, ST Microelectronics, etc. The surface of these ICs coated with resin, so it was really hard to read the product numbers written on the ICs. Next, I'll explain the circuit structure. A circuit board is on top of another. I'll go into the details of each board later. First, I'm going to explain how the input current flows on these 2 boards. These are the DC input busbars. One is positive and the other is negative. The busbars are soldered to this top board directly. There are capacitors on the top board. The voltage is smoothed by the capacitors. After that, how is the voltage supplied to the bottom circuit board? This is quite important. Let me remove the capacitor board. There. Now you can see the bottom board. Let's have a look at the back side of the capacitor board. In these areas, copper foils are exposed around the holes. Now let's look at the bottom circuit board. Let's zoom in. There are aluminum collars. Each of them has positive, and negative polarity. The collars on the bottom inverter board and the copper foils on the top capacitor board come in contact with each other when you place the capacitor board on the inverter board. When you press the capacitor board against the inverter board, the DC voltage is supplied from the capacitor board to the inverter board. Many power semiconductors are mounted on this board. This is the inverter circuit. If you remove this bus bar, you can find collars here. There are 3 bus bars. They all have collars underneath. These bus bars are the outputs of 3-phase AC. The input DC voltage is converted into 3-phase AC voltage by the inverter. From here, the AC voltage comes out. Let me put the board back on. After the DC voltage comes in, the voltage is supplied to the inverter board through the collars because the 2 boards are pressed against each other. Then the voltage is converted by the inverter and the AC voltage comes out from the 3-phase outputs. And the outputs are connected to the backside of this cover. The structure is pretty much thought through. There are holes in this capacitor board. When you put the capacitor board on the inverter board, the capacitor board doesn't have any electrical connections with the bus bars on the inverter board. It may be easier to understand if you look at the board from this side. This is the DC input bus bar. The DC voltage is supplied from the bus bar to these exposed copper foils. The collars on the bottom inverter board are pressed against the copper foils to establish current paths for the DC voltage. These electrolytic capacitors manufactured by Aishi withstand 105 degrees. Their capacitance is 220 microfarad and withstand voltage is 160 volts. 22 electrolytic capacitors are connected in parallel. Instead of using one electrolytic capacitor with a large capacitance, many capacitors with a small capacitance are connected in parallel. I guess this method was chosen to lower the ESR. These electrolytic capacitors are likely to generate heat, so they are placed with some space between them. This pink anti-vibration rubber sheet we saw earlier is placed on the capacitors. The sheet covers the pressure relief valves, but it's not pressed strongly against the capacitors. So I guess it's not so much of a problem. This is a film capacitor for an electric car. Recently, electric car battery voltage is high, so a film capacitor is essential for such cars. However, this electric car's battery voltage is only 96 volts. Therefore, aluminum electrolytic capacitors can be used. Film capacitors are commonly used for electric cars to smooth voltage also because film capacitors have low ESR. But this electric car's battery voltage is only 96 volts. So considering the cost, aluminum electrolytic capacitors were the best to use, I suppose. Let's zoom into this electrolytic capacitor board. Can you see this bus bar? This bus bar is used to secure the current carrying capacity. There are 3 bus bars on this side and 3 on the other side as well. To check the material of this bus bar, I scratched the surface a little. You can see the copper color. The right half of this board is a gate driver circuit. It drives the MOSFETs on the inverter board. They are connected using this connector. There are film capacitors close to the gate driver circuit. The inverter circuit converts the DC into AC. In the process, some noise or voltage ripples are generated. To prevent the influence from such noise, these film capacitors are mounted near the gate driver circuit because they can filter the high frequency component. They are placed closely. There are DIP components here. These are gate driver ICs manufactured by Broadcom. At the outputs of the gate drivers, there are diodes and gate resistors. The gate driver characteristics are changed when the MOSFETs are turned on and off. Finally, let's go into details of the 3-phase inverter board with power semiconductors. This is the board with power semiconductors. It's made of aluminum. As I said earlier, this inverter board is attached to the heat sink and cooling fins. The heat is conducted in the order of the power semiconductor, solder, copper foil, insulating layer, aluminum layer, thermal grease, and then heat sink. The heat sink is good enough to handle this amount of heat. The power semiconductors on this board are silicon N-channel MOSFETs made by Infineon Technologies. The rated voltage and current is 150 volts and 100 amps. 36 MOSFETs are used in total. I drew these red circles to indicate the places where N-channel MOSFETs were mounted. The MOSFETs were removed before I disassembled the inverter, so I marked where they were. There are 36 power semiconductors in total. They are connected in parallel with 6 per arm. One leg consists of 12 MOSFETs. There are 3 phases, so 36 in total. Since they are connected in parallel, the current won't be distributed equally. But it seems possible to apply the rated momentary current of 350 amps. As for the manufacturers, the gate driver ICs, MOSFETs, and the microcontroller for the control board are made by renowned Western manufacturers. Of course, gate driver ICs and MOSFETs made by Chinese manufacturers would work. But Western manufacturers with a proven track record were chosen even if their products are more costly. I think it's because they are more reliable. The MOSFETs on this board are not mounted at one place. They are placed sparsely. It's for heat dissipation. The capacitor board is placed on top like this. In the area where capacitors are mounted, MOSFETs are placed relatively sparsely. On the other side of the board, they seem to be placed a bit more densely. Let's go into details of this board. These are the DC inputs. I painted the colors red and blue so you can tell the polarity. From the left, positive, negative, and negative inputs. Then there are three-phase outputs here. I'll call the outputs U phase, V phase, and W phase. This is the leg for the U phase. This is the leg for the V phase. And this is the leg for the W phase. This is the high side arm for the U phase, and this is the low side arm for the U phase. This is the low side arm for the V phase, and this is the high side arm for the V phase. This is the high side arm for the W phase, and this is the low side arm for the W phase. If you look closely at the board, you can see that bus bars are mounted here, here, and here. A bus bar that's thicker than the others is used here. It's probably to increase the current carrying capacity. I wonder why these bus bars are placed in an asymmetric way on this board. The important factors that affect the placement of the bus bars are the DC input arrangement and the MOSFET arrangement. First, let's look at the high side of the U phase. Here, only U phase current flows. Moreover, the drain tabs of the MOSFETs are mounted, so the copper area is large, which means the current carrying capacity is high. Next, let's look at the low side of the W phase. Only W phase current flows here as well. Since the source pins of MOSFETs are mounted, the copper area is relatively small. I think that's why this bus bar is mounted here. It's to increase the current carrying capacity. Next, let's have a look at this part where the high side of the V phase and W phase meet. Here, both V phase current and W phase current flow. So the power loss is bigger. In order to let both currents flow, you need to secure a large current carrying capacity. I think that's why a thick bus bar is used between the V phase and W phase. Then let's look at the low side of the U phase and V phase. Here, the source pins of MOSFETs are mounted. So the copper area is small, which means the current carrying capacity is small. However, for some reason, a thin bus bar is used here. While disassembling this inverter, I was thinking that these bus bars should have been swapped. The bus bar here should have been thicker, and the bus bar here should have been a little bit thinner. But for some reason, the bus bars are arranged in this way. I've been thinking why these bus bars are arranged in this way. I tried to forcibly come up with a convincing reason, and realized it might be the placement of the cooling fins. I turned the heat sink over. Considering the inverter's position, the air from the outside comes in from this direction. The air flows from the left side to the right side of the screen. Then, you can say that the U phase area is sufficiently cooled down. On the other hand, what about the W phase? The fins are not long enough to reach the W phase. Furthermore, the air comes in from this side. The W phase is less cooled by the air compared to the U phase. Maybe that's why the bus bar on the W phase is thicker. I tried and came up with this idea. Well, I'm not sure if it's true. When I announced on Twitter that I was going to disassemble this inverter, I received a comment saying the inverter is very similar to the ones used for forklifts. So I got an inverter that's used for forklifts and such small mobile vehicles here. This is an AC inverter made by Curtis. It is also a three-phase inverter. Let's take a look inside. At the first glance, you can see the similarity. These are the three-phase output bus bars, and these are the DC input bus bars. Two circuit boards are used. I'll remove the top one. It looks so similar. Many electrolytic capacitors are connected in parallel. There are DC input terminals. The current paths are established by pressing the collars against the terminals in the same way as the electric car inverter. The same goes for the three-phase bus bars. The current paths are established by pressing the bus bars against the terminals. There are only two current sensors like the electric car inverter. Hall sensors are used. A Hall sensor is secretly hidden here. The microcontroller calculates the current of the remaining one phase using the two current sensors for the other two phases. Similarly, the MOSFETs are mounted on the aluminum board. The main body serves as a heat sink. The board conveys heat to the heat sink using the thermal grease. The heat is conducted in the order of the MOSFET, solder, copper foil, insulating material, aluminum board, thermal grease, and then the aluminum heat sink. Very similar to the electric car. Although the structure is not exactly the same, there are many similarities. For example, many aluminum electrolytic capacitors are connected in parallel. The aluminum collars are pressed against the board to serve as conductors. The power semiconductors are mounted on the aluminum board. There are only two current sensors. Pin headers are used to connect the circuit boards. Such similarities were found. In order to sell this inverter at a low price of 28,800 Chinese yen, the development cost must be held down. This is all my guess, but I think they reused the design concept and structure of small mobile vehicle inverter circuits with already proven results to lower the development cost. However, the design is a bit changed to output high power for the electric car. The circuit is a bit larger. To protect capacitors from vibration, a rubber sheet is used. So today I disassembled the inverter used for extremely cheap electric cars made in China. To state my impression after disassembling the inverter, the design is borrowed from small vehicles with proven results. And as for the important semiconductor components, renowned Western manufacturers are used. But for other passive components, Chinese manufacturers are used. This inverter is made at low cost, but ensures a certain degree of reliability by using high-quality semiconductor components. That's my impression. I disassembled this inverter today, but Professor Yamamoto, who lent me this inverter, has many inverters of other car models. In the future, I want to disassemble some of his other inverters and make videos. Thank you for watching. If you like this video, please hit the like button and subscribe to my channel.